ICT equipment depends on more than just software and network connectivity. It depends on a set of physical utilities including power, cooling, and telecommunications that must be continuously available for information systems to function. Control A.7.11 of ISO 27001, 2022 requires organizations to protect these supporting utilities from failure, interruption, and damage. In the next few minutes, we will explore what this control requires, why utility resilience is a core information security concern, and how we design utility protection systems that keep our infrastructure running. Let us begin by identifying the utility types covered by Control A.7.11 and the security risks that utility failures create for information systems. Control A.7.11 requires that ICT equipment is protected from power failures and other disruptions caused by failures in supporting utilities. The supporting utilities that ICT equipment depends on span a wider range than most people initially consider. Electrical power is the most obvious. Without it, equipment simply stops working. But cooling is equally critical. Server rooms and data centers generate substantial heat, and without functioning air conditioning and ventilation, equipment will overheat and fail within minutes to hours of cooling loss. Telecommunications infrastructure, both internal network cabling and external internet and voice connectivity, is a utility dependency that affects the organization's ability to communicate and access cloud-based services. Water supplies may be relevant where liquid cooling systems are in use. Each utility represents a potential single point of failure that must be addressed in the utility protection design. Uninterruptible power supply systems are the first line of defense against power disruption. A UPS provides battery-backed power that activates instantaneously when mains power fails, giving equipment time to continue operating or to shut down gracefully without data loss. UPS systems are rated by their capacity, the amount of power they can supply, and their runtime, how long they can sustain that power from battery alone. For critical systems, we design UPS capacity to provide sufficient runtime for backup generators to start and take over. Regular testing of UPS systems under load is essential to verify that they will perform as designed when needed. Cooling failure is one of the most common causes of unplanned data center outages and one of the fastest acting. A server room without cooling can exceed safe operating temperatures within minutes in warm weather. Redundant cooling systems, typically achieved through N+1 or 2 N configurations where additional computer room air conditioning units are available to take over if a primary unit fails, prevent cooling loss from becoming an outage. Hot aisle and cold aisle containment architectures improve cooling efficiency and reduce the risk of hot spots that could cause localized equipment failures even when the overall cooling system is functioning. Utility monitoring provides the real-time visibility that enables us to detect and respond to utility problems before they escalate into equipment failures and service outages. Power monitoring tracks voltage levels, current draw, and UPS battery status. Temperature and humidity sensors detect cooling degradation before equipment overheating occurs. Water detection sensors identify leaks from cooling systems or roof drainage before they reach equipment. Telecommunications monitoring detects link failures and connectivity degradation. Alerts from these systems should reach facilities and IT operations teams immediately, with escalation paths that ensure response even outside business hours. For technical concepts that are central to designing and managing utility protection systems under Control A.7.11. Uninterruptible power supply systems protect against 3 distinct power quality threats. Complete power outage, where the electricity supply fails entirely, power sags and surges, where voltage drops or spikes can damage equipment or cause unexpected resets, and brownouts, where sustained low voltage can stress power supplies and cause intermittent failures. A well-specified UPS addresses all 3. For critical systems, the UPS should be sized to power all connected equipment at peak load for the time required for backup generators to start, typically 2 to 5 minutes, plus a safety margin. UPS batteries degrade over time and must be tested and replaced on a schedule to ensure they retain their rated capacity. N+1 redundancy is a design principle that appears throughout utility infrastructure design. For a server room with 4 cooling units where 3 are required to maintain safe temperatures under peak load, an N+1 design provides for units, 1 more than needed, so that if any single unit fails, the remaining 3 can maintain cooling without any degradation. The same principle applies to power feeds, UPS units, generators, and network circuits. The cost of N+1 redundancy is the additional capital and operating cost of the spare capacity. The benefit is that no single failure causes a service outage. For critical infrastructure, 2N redundancy, twice the required capacity, provides protection against 2 simultaneous failures. The Uptime Institute Data Center Tier Classification System provides a standardized vocabulary for describing and comparing the resilience of data center infrastructure. Tier 1 provides basic capacity with no redundancy and 99.671% availability. Tier 2 adds redundant components. Tier 3, concurrently maintainable, adds redundant distribution paths and 99.982% availability. Tier 4, fault-tolerant, provides full 2N redundancy with 99.995% availability. Understanding where our facilities fall in this classification helps us communicate the utility resilience we provide to stakeholders and identify gaps relative to the availability requirements of our most critical systems. Power distribution units are the final link in the power delivery chain from UPS or generator to individual servers and network equipment. Intelligent PDUs provide per-outlet power monitoring and control, enabling facilities teams to see the power consumption of individual equipment items, identify circuits approaching their capacity limits, and remotely power cycle equipment that has become unresponsive. Dual-corded equipment, servers and storage systems with 2 power supplies, should be connected to PDUs on separate UPS circuits so that the failure of one UPS or one PDU does not power down the equipment. Proper PDU architecture is a detail that significantly affects the resilience of the overall power protection design. Now let us explore how we test utility protection systems and how data center tier ratings provide a framework for measuring utility resilience. Regular testing of utility protection systems verifies that they will perform as designed when a real failure occurs, providing the assurance that monitoring and documentation alone cannot. UPS testing under real load conditions is the only reliable way to verify that battery capacity and transfer time meet design specifications. A UPS that has never been tested under load may appear healthy, batteries showing full charge, management software reporting normal status, yet fail to sustain load for its rated duration during a real outage because battery cells have degraded without obvious external indicators. Full load tests, conducted during planned maintenance windows with appropriate change control, subject the UPS to the actual conditions of a power failure and reveal any shortfalls in capacity or transfer speed before those shortfalls cause a real outage. Generator testing must be more than just a monthly no-load start. It must include a periodic full load test that simulates an actual grid failure and requires the generator to supply the facility's full operational load for an extended period. This type of test reveals fuel consumption rates under real conditions, identifies thermal issues that only emerge under sustained load, and verifies the automatic transfer switch that connects the generator to the facility's electrical distribution when mains power fails. Fuel supply checks should verify not only that sufficient fuel is on site, but that the fuel is in good condition and that supply agreements are in place to deliver additional fuel promptly if an extended outage requires it. Utility monitoring systems are only as effective as the alert configurations that connect sensor readings to human response. Alert thresholds that are set too conservatively generate alert fatigue, causing real alerts to be ignored. Alert thresholds that are set too liberally miss developing problems until they become failures. Alert routing that sends notifications only to email addresses that are not monitored outside business hours provides no coverage during nights and weekends, when many utility failures occur and when data centers with reduced staffing are most vulnerable. Reviewing alert configurations as part of a regular testing program ensures that the monitoring system will reliably deliver timely alerts to the right people when it matters. Data center tier standards provide an objective framework for assessing the resilience of utility infrastructure and communicating that resilience to stakeholders. Aligning our facility design with the appropriate tier for the criticality of the systems it houses provides a benchmark against which we can measure and report utility resilience. For an organization hosting critical operational systems, a Tier 3 facility design, with concurrent maintainability and 99.982% availability, may be the minimum appropriate standard. For less critical infrastructure, Tier 2 may be sufficient. Documenting the tier alignment of our facilities in our ISMS demonstrates that utility protection decisions are made systematically against recognized standards. Let us consolidate the essential points from our exploration of control, A.7.11. If you want to master all 93 ISO 27001, 2022 Annex A controls and build a certification-ready ISMS, our complete Udemy course provides the implementation guidance, templates, and practical examples you need. Enroll today. Thank you for watching. If you found this helpful, please like and subscribe for more ISO 27001 control explainers. See you in the next video.